Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Shafi bin Ahmad Kamali, matrix number GS70527, and this is the presentation for laser diffraction static light scattering. Before I further present my presentation, I will break down my presentation into six subtopics, which are the principle of laser diffraction, the equipment, the data interpretation, the limitation of laser diffraction, the error source, and also some of the case study. When monochromatic, coherent, and polarized light strike an object, it's either refracted, absorbed, and re-radiated, or diffracted. Reflected occur when incident beam change in direction to the light source. The refraction occurs as light changes angle traveling through the particle, while absorption and re-radiated occurs when particle absorb light and re-radiate at certain angle, but not the same with refracted angle. Diffraction occur when light change angle and not travel through the particle. Previously, we know that there are several types of interaction occur when light strikes a particle. One of the interaction is light diffracted through the edge of the particle and it will generate a certain angle. The diffraction of light actually can be understood by Young's experiment. Young is illustrate how light can be diffracted when it passes through a certain obstacle. He created two small slits and passed the light through it. Then the reflected light is projected to a screen in order to see the pattern of light. A pattern of bright and dark fringes appears on the screen due to the interferences of light wave coming from these two sources. Interference is the phenomenon in which when waves are superimposed and they are reinforced or cancel each other. We know that light is diffracted and it was proved by Young experiment, but the light is not diffracted only by a slit. It can also be generated by pass the light through a pinhole. It is also can be diffracted when it goes through a particle. Based on this, it is easily assumed that light can be diffracted through a particle and it will produce a certain angle. Then it is possible to measure a particle size by measuring its diffraction angle. Since the particle size can be measured by its diffraction angle, meaning that we need to calculate the related parameters. This can be described by a formula. The diffraction of light are determined by using n lambda equal to d sine theta, where d is spacing between the adjacent slits, theta is the angle of diffraction, lambda is the wavelength of light, and n is the order of diffraction. Based on this equation, the disk spacing of slit is actually represent the particle size. By calculating the disk spacing, meaning that the particle can be calculated as well. There is a relationship between size of particle and also the angle of its diffraction. Angle of diffraction is inversely proportional to particle size. Small particle will diffract at a larger angle than the large particle. The amount of light scattered or the intensity is directly proportional to the particle size. Larger particles scattered more light than small particle and it will exhibit sharper peak. There are two theories that perfectly describe the principle of light diffraction. First is Fraunhofer theory. According to this theory, the angle of laser beam and particle size have an inverse relationship. This theory does not require any knowledge of the optical properties. As particle size decreases, the angle of laser beam increases and vice versa. Good for the measurement of particles bigger than 50 micron. And the assumption by this theory is all particles are larger than the light wavelength, and the second one is only consider the light scattering come from diffraction phenomenon. Another theory to describe about light diffraction is the May theory. May theory demonstrates how the absorption ability of particle will impact the amount of light. The ability of particle to absorb light will affect the diffraction of light. It is necessary for the measurement of particle larger than 5 micron. May theory requires knowledge of optical characteristics of both the sample being examined and the refractive index of the dispersant. And light must be collected from over a large range of angle and it is assumed particle in a sphere shape. And now we are going to looking at the equipment of laser diffraction. Basically, laser diffraction is divided into three units, which are optical bench, the sample dispersion unit, and also the instrument software. Optical bench is a dispersed sample pass through the measurement area of the optical bench where a laser beam illuminates the particle. A series of detectors that accurately measure the intensity of light scattered by the particle within the sample over a wide range of angle. And then the second one is sample dispersion unit. Sample handling and dispersion are controlled by sample dispersion unit where it is designed to either measure the sample wet or dry. It will deliver this measurement area of the optical patch at a stable state of dispersion. And then the third one is by instrument software. The instrument software control the system during the measurement process and analyze the scattering data to calculate the particle size distribution. Okay, okay. Now we are going to discuss for the data interpretation. When we have a data from the laser diffraction instrument, we will have to analyze the data. There are several data that we can use to analyze the data. First, first is a mode in model model. The mode is defined as the most commonly occurring size. This frequency distribution curve having one big and narrow because it's containing only particles of very similar size. Second one is bimodal. Bimodal is used when characterizing polys per sample. It can be seen if there is two samples having similar mode but different size distribution. And the third one is the median. Median is the value separating the higher half of the data from the lower half. The median is easy to determine from the cumulative distribution curve. Another another technique we can use mean particle size according to moment ratio. There are several types of mean method that we can use. For example, we can use number weight mean, and the formula is shown there. And we also can use the surface weight mean, and by using the different formulation here. And it is depends on the application that we want to use. For example, if we want to use the number weight ratio, we can use it for the application of biological application like viruses or blood cell counting. If we want to use surface weight mean, it is suitable for catalysis and field compression and etc. Okay, there are several applications for laser diffraction in the industry. For example, like pharmaceutical use the laser diffraction to get the information or the particles information for drug formulation, which affecting the solution rates, bioavailability, and also the stability. In food and beverages, particle size play a significant role in the texture, taste, and stability of food products. Meanwhile, in cement and building material, particle size of cement and other building material influence the strength, setting time, and durability of the final product. In cosmetic, the particle size affect the feel, application, and appearance of product, cream, and solution. Laser diffraction also face some limitation. The main limitation that faced by laser diffraction is broken particles. The broken particle is due to the excessive ultrasonic energy or excessive air pressure in sample preparation. The ultimate goal for laser diffraction is to measure the primary particle size so that we have to avoid the degradation of the primary particle. The ultrasonic energy can disperse agglomeratic primary particulate in liquid suspension, but applying excessive ultrasonic energy can cause primary particle to fracture in some cases. Also, the effect of air pressure as a dispersion method for dry powder must be monitored carefully. The pressure chosen must be sufficient to fully disperse the primary particulate. Picture here show that at the left side, the primary particle observed under 100 micron microscope. Okay, the right side is when we apply excessive energy by using the ultrasonic, the primary particle broken into smaller particles. So this means that when we apply extra energy in our particle, it will degrade the primary particle itself. Okay, the second limitation faced by laser diffraction is the presence of bubble peak. Bubble peak are commonly observed in laser diffraction result. Operator of the instrument should be trained to identify and minimize a bubble problem before collecting any data. Even when all necessary precautions are taken, bubble peak can occasionally appear in liquid dispersion data. It is important to be able to identify this peak as distinct from particulate to be measured. A simple check under a microscope is often sufficient to rule out the presence of particulate in the size range of the suspended bubble peak. For example, here we can see there is a small peak above 100 micron. When we take the same sample and observe under the microscope, there is no particulate size over 100 micron. That means the bubble peak is present in the sample during the laser diffraction analysis. So, laser diffraction is always need secondary instrument to confirm the result. confirmation by microscope. Examining the sample under a microscope is a critical step in verifying the result obtained by a particle size analysis correspond well to the observed particle size. When the particle size distribution of material need to be measured, steps should be taken to ensure that the measured data output reflect the test sample rather than an artifact, bubble, or other source of data contamination. Okay, next we are going to discuss about error source from uh, laser diffraction analysis. Uh, First, error source may come from the sampling itself. The sample must be representative of the bulk of the material. Sampling becomes the largest possible source of error in the measurement of coarse particle or sample containing a broad range of sizes. Laser diffraction is a volume-based technique. It is extremely sensitive to small changes in the amount of coarse particle within the selected sample. And then the reproducibility increases the volume of sample required to measure representative sample of the coarse particle fraction. It is necessary to measure a large sample, often greater than 1 to 2 grams, to ensure the reproducibility of the result. Okay, the second error source may come from the dispersion. The selection of dispersion must be made carefully. The dispersion must be provide good wetting of the sample, not dissolve in the sample, not contain bubble, have a suitable viscosity, be transparent to the laser beam, have a different refractive index to the sample, be chemically compatible with the material used in the instrument. The use of dispersion of opposite polarity is always recommended, and the most commonly used dispersion is water. However, water is not suitable for every sample, whether due to the poor wetting or dissolution of the sample. Next, the error source is also may come from the dispersion of powder in liquid. There are three steps to disperse our powder sample in the dispersion. First is wetting the sample. Second is adding the energy to improve dispersion, and the third one is stabilizing the dispersion. By wetting the sample, good wettings between particle and dispersion shows a uniform suspension of particle in the liquid, but poor wetting may show droplet of liquid on top of the powder or significant agglomeration and sedimentation. By adding the energy, it will improve the dispersion of sample in the dispersion. And then stabilizing the dispersion, re-agglomeration of sample may occur. An additive be required to stabilize the dispersion. Additives such as sodium hexametaphosphate, ammonium citrate, and sodium pyrophosphate can help to stabilize the suspension. Okay, error source also can become from the instrumentation part. For example, the obscuration range. The obscuration range is the percentage loss of laser light through the sample. The appropriate sample concentration for a laser diffraction measurement is called as obscuration range. Too much sample cause the measurement is affected by multiple scattering, but too low sample concentration cause insufficient to overcome the signal to noise ratio or a representative sample of the bulk material. The measurement duration also is important. That contribute to the error source. The measurement duration need to be long enough to allow a representative sample to be analyzed. And the stir speed also may contribute to the error source. The stirrer inward dispersion unit must ensure this dispersion is homogenized while passing through the measurement cell. You need to carry out a stir speed titration to check that all of the particles in the sample have been suspended before analyzed. Okay, now we are going to discuss one of the case study about particle size analysis to control the product properties of cement. There are three stages for the production of finished cement. The preparation of a raw mix, production of the clinker, and the grinding of the clinker to form a finished cement. And the raw mix can be made up of materials such as calcium oxide, silicon oxide, and oxide. These components are then ground into a raw mix, but not more than 15% of the volume or mass particles are larger than 90 micron. The proportion of coarse particle in the raw mix must be controlled to ensure that the resulting mix is homogeneous and that sintering of component during the next stage of production is complete within a reasonable time frame. As we can see here, the size distribution about for 90 micron, below the 90 micron is only below 2.5% only. The cement strength, the critical strength and curing properties of cement are dependent on the particle size distribution resulting from the grinding phase. The comprehensive strength and curing qualities are increased as the particle size decrease due to the increase in surface area. In general, cement between 60 and 70 is between 3 micron and 30 micron in size. Excess large particle greater than 50 micron can cause problem by reducing strength due to incomplete hydration, whereas excess small particle, which is less than 2 micron, can reduce strength and can cause the cement to crack by setting exothermically. As we can see from the result here, the distribution of particle size within 3 to 30 micron is around 65 percent. That's all for my presentation. Thank you for your attention and bye bye.